Hello and welcome back. We are in section 7.2, simplifying trig expressions. Very similar to simplifying algebraic expressions, except we can usually with our trig stuff go a little bit farther because of our identities. So let's take a look at this. Number one, I can see that I am multiplying sine x times the difference of cosecant x and cotangent x. Very similar situation here. On the left, we distributed. We can also distribute right away in this trig expression. You don't have to, but I want you to see the similarities between the two. So if I multiply, I then have sine x cosecant x minus sine x times cotangent x. Okay, now in algebra we stopped, but here we don't necessarily, or stopping isn't the best, going to be the most simplified. So what are we going to do? If I look here when I'm multiplying, two things to recognize. Sine and cosecant are reciprocals. For example, it's like saying 5 times 1/5. What happens when you take 5 times 1/5? You get 1. That's the idea with reciprocals. They are multiplicative inverses of each other. Okay, so you could go straight to, if you recognize that, you could go straight to 1. Okay, but the other thing we did, and we did it quite a bit in section 7.1, is when we were dealing with trig expressions, one of the things we would do is write everything in terms of sines and cosines. So you could do that here as well. Cosecant, remember, is 1 over sine. So I'm taking sine x times 1 over sine x. So when I multiply, the signs divide out and I end up with 1. Okay, here I can rewrite cotangent as cosine of x over sine of x. And then when I multiply by sine of x, remember sine is over 1. So I typically always cross cancel or divide out common factors diagonally, okay, before I multiply, especially when I have algebraic expressions or trig expressions such as this. So when I multiply here, I'm left with just cosine x. And 1 minus cosine x, that is simplified. That I cannot do anything else. Okay, so I'm ultimately saying this original expression is equivalent to 1 minus cosine x. So if I would substitute in angles for an angle for x in each side, as long as it's an angle that is in the domain of cosecant and cotangent, I should get a true statement. Okay, so let's look at another situation where here we were multiplying two binomials on the left. Notice how these are conjugates, a sum and a difference of the same two terms. So we know if we do FOIL, when we do the outside and the inside products, they're opposites and they add up to be 0. That's why we have no middle term. So remember, when I multiply conjugates, I end up with what's called a difference of two squares. I don't know what happened here. Whoops. Somehow I got an extra page. Okay, so once again over here I can see a similar situation. I've got a plus and a minus. So all I have to do here is multiply the first terms or square the first term. So I get cotangent x times cotangent x is cotangent squared x. And I multiply the last term, so that becomes cosecant squared x, and it's a minus in the middle. Okay, so in algebra we stopped, but in trig, I know I have an identity that involves cotangent squared and cosecant squared, one of our Pythagorean identities. And let's see if we can rewrite that in an equivalent, more simplified expression. So my Pythagorean identity is cotangent squared x plus 1 is equal to cosecant squared x. So what I want is I want cotangent minus cosecant. So if I rearrange this so one side has this on it, then I can replace this expression with the other side. So I'm going to subtract cosecant x, basically move it to the left, and subtract 1 on both sides and move it to the right. So I can rewrite this in the equivalent form as cotangent squared x minus cosecant squared x equals -1. Okay, so that means I can replace cotangent squared x minus cosecant squared x with -1. So if I do that replacement, this is much more simplified than that. Okay, now do you have to do that? No. Could you stop here and have it be equivalent? Yes. So the idea with these simplifying these trig expressions is ultimately you're practicing for when you're proving identities. We just don't have a lot of time to do that since we lost a week. So it would just depend on what you needed to do. You may be able to stop at cotangent squared minus cosecant squared. You may need to get to -1. Depends on what the identity is that you're proving. So either of those are acceptable. Okay, squaring a binomial. There's two ways. You can do the old write it out or take it times itself, do the foiling or distributing, combine like terms. That's where you get this middle term. It's combined of the outside, which is AB, and the inside, which is AB, which gives us 2AB. Or you can use the formula, which I call it the shortcut, which is basically just square the first term, square the last term. Both of those are always positive. And to get the middle term, you take the first times the second, A times B, and you double it. So it doesn't matter which method you use to me as long as you can come up with that perfect square trinomial. Okay, remember that's what we call it. So I'll do one way and do the other one the other way. So let's take 1 minus tangent squared beta, and let's go ahead and write that out and go ahead and distribute or FOIL. So that's 1 minus tangent beta times 1 minus tangent beta. Take it times itself. And then do our four multiplications. 1 times 1 is 1. 1 times negative tangent beta. Negative tangent beta times 1. Negative tangent beta times negative tangent beta is positive tangent squared beta. Combine like terms, and the two terms here in the middle. And so I'm left with 1 minus 2 tangent beta plus tangent squared beta. Okay, now could you stop here? Sure. Okay, but there might be something else that we could do to simplify this. When I see a tangent squared and I see a 1, which makes me think Pythagorean identity. So maybe I can rewrite that in an equivalent form. And I know that I could rewrite those next to each other if I wanted. I could write that as, well, actually, I don't know that I have a lot of room, so let's don't do that. All right, so 1 plus tangent squared beta, that's Pythagorean identity, which is equivalent to secant squared beta. Okay, so I'm replacing those, and then I have minus 2 tangent beta. So this is another form that is equivalent. Once again, depends on what you're going to do with it. In my math lab, I believe most of them are multiple choice, so you'll look for the one that's like yours, or if not, figure out if you can go a step farther. Okay, so here's another one where we square. So let's use the shortcut. So basically, I have, this is like saying take the binomial a plus b and square it. Okay, so here our a is cosine and our b is sine. And remember, our formula is square the first term. Okay, so that means then I'm going to take the first term cosine and I'm going to square it. So I get cosine squared x. Okay, then if this is a sum, then this one is also a sum. Okay, to get the middle term, I multiply the first and the second together, so I get a times b, and then I multiply it by 2. So I'm going to do the same thing here. I'm going to take cosine times sine and multiply it by 2. And this is a plus, therefore this middle term is a plus. Okay, and then finally I take the second term here, b, and I square it. And notice how I put a plus there because no matter what, if that was a minus in front, I would be squaring a negative, which is a positive. So in a perfect square trinomial, the first term and last term are always perfect squares. So I'm going to put a plus here. And then I'm going to square the second term. The second term is sine. So I'm going to square sine and get sine squared x. Okay, so now I look at this and I think, well, could I write this in a more simplified form? Well, yes, I can, because what's cosine squared x plus sine squared x? That is equal to 1. It's a Pythagorean identity. So I can rewrite that as 1 plus cosine x sine x. Now, that is good, okay? For fun, we could actually go a step farther and rewrite this right here. 2 cosine x sine x, or 2 sine x cosine x, is also equal to sine of 2x using a double angle identity. But I don't believe my math lab would do that because technically we didn't learn double angle till 7.4. So they're all equivalent though. That's the idea. So it's just whatever you might need, what might help you. The cool thing is if I think about that for a second, think about if this was an equation. 1 plus 2 cosine x sine x, and it was equal to 0. Okay, so solving this in the form that it's in is a problem because I can't factor it. The only other thing I could do then would be to use my identity replacement. And if I do replace that with sine of 2x, then we could solve it by isolating the trig function. If you haven't seen the videos for 7-6, there's a video about multiple angles, and then you would know how to solve that equation. So sometimes writing things in different forms helps us with solving equations as well. All right, what's our next one? Oh, okay, cool. How about you try this one? So what I would like you to do is please pause the video and see if you can perform those operations and simplify that result. All right, so you want to see the solution? You can compare it to your answer. So here we are once again squaring a binomial, which is multiplying or distributing. Okay, so you can write it times itself or do the shortcut. I like the shortcut. You should get comfortable with the shortcut. It'll make it very easy for you. Okay, shortcut says square the first term. So 6 squared is 36. The middle term is a minus. And then to get the next term, I take 6 times cosine x and I double it. So if I have 6 cosine x times 2 is 12 cosine x. And the last term I the same thing you should have gotten if you took it times itself and distributed or FOILed. Okay, so then I have plus sine squared x. Okay, now, can we combine like terms? I don't see any like terms. Can we rewrite something different using an identity? And here it is again. Good old Pythagorean identities. This is the one. So I basically have 36 minus 12 cosine x plus 1. If we combine our like terms, we end up with 37 minus 12 cosine x. All right, so this expression is equivalent to this original expression. So it is a bit more simplified. For example, if I had to plug something in there for x, it would be less work. Okay, so now factoring. This will come in handy in 7.6 when you're solving equations. So most people are pretty good at factoring these trinomials. Remember, a trinomial in this form, the form, we say ax squared plus bx plus c, highest power is 2, descending order. If it's factorable, it'll always factor into two binomials. All right, so basically multiply to be -3, add up to be -1. And the reason that works is because the leading coefficient is a 1. Okay, if you can factor this trinomial, then just transfer it over to here. Do you see the same pattern? Okay, so instead of x, I have cosine beta. So this is like saying cosine beta squared minus 2 cosine beta minus 3. So it's kind of like using, we could think of that u substitution, or we've talked about replacing it. So this is where your x would have been. So it would have been x squared x3. Okay, so if you need to do that substitution, choose a different variable for your trig function and then factor and then go back to your trig function. Okay, so instead of x and x, I have cosine beta, and same thing, multiply to be -3, add up to be -2. So +1 and -3. So there are my factors. Okay, now this is the one that causes stress for lots of people. Okay, when the leading coefficient is not a 1, you can't do multiply to be -5, add up to be 2. It might work once in a million by chance, but it does not work all the time. There are other methods to use besides AC grouping. I know there's some fancy little trick methods that work. I don't care what you use as long as you can factor those trinomials with the leading coefficient of 1. I did put a video in D2L. I put the link in, well, it's a link to a YouTube video on a refresher on how to do that. Otherwise, come see me. We could go over it in class. If you come to a class meeting, come see me virtually in my WebEx math room. All right, so can you see how it's very similar here? Instead of x, we have sine of y. So if you need to rewrite it, do so. Okay, so 3 sine squared y would be 3 sine y and sine y. That would multiply to be 3 sine squared y. And I know then that this has to be a +5 and this has to be a -1. Okay, so the big thing here is maybe convert it into something in terms of just a variable rather than a trig function. All right, difference of squares. Now we're going the other direction. A little bit ago, we went from multiplying to this. We're now going to go factoring. We're going to go back. So recognizing that you have a difference of squares, perfect squares. So 9x squared is a perfect square. There is something that I can square to get it. I can square 3 to get 9, and I can square x to get x squared. So notice the 3x will be my first term. Whatever you square to get the y, the second term, the 4y squared, 2y will be the last term. So same idea over here in terms of trig. I know that 9 is a perfect square and secant squared is a perfect square. So the first terms of my binomials will be 3 secant theta. Okay, and a difference of two perfect squares factors into binomials with different signs. They're called conjugates. Doesn't matter where you put the plus or the minus. Okay, whatever you square to get 4 tangent squared will be your second term. So what do you square to get 4? 2. And if you square tangent, you get tangent squared. Those will be your second terms. All right, and I don't think I can do anything here. We might be tempted to think Pythagorean, but this is to the first power, not squared, so we can't use a Pythagorean identity. All right, now this one's tricky. It's still a difference of two squares. If the power is even, it's a perfect square. So what do you square to get m to the fourth? Well, 4 divided by 2 is 2. So if I square m squared, I get m to the fourth. If I square k squared, I get k to the fourth. So basically, it's a difference of two squares. So sum difference of m squared and k squared. Now, the trick here is, notice that this is another difference of two squares. So it can be factored into conjugates again, sum or difference of terms. Okay, this is a sum of squares, does not factor into real numbers. So we'll just say it is not factorable. Okay, now going over here, so I have basically cosine to the fourth of theta. If you need to, rewrite it like this. That's the cosine of theta raised to the fourth power. Sine of theta raised to the fourth power. Okay, so then I recognize that these are perfect square, difference of two squares. So I'm going to factor it into two binomials with different signs. So what do you square to get cosine to the fourth? Cosine squared theta. That would be my first terms. What do you square to get sine to the fourth? Sine squared theta. Those would be my second terms. Okay, now here we can go a little bit differently because over here on the left, I couldn't factor m squared plus k squared, and I can't factor cosine squared theta plus sine squared theta, but we know that it is equal to 1. How many times have we seen Pythagorean identities today? A lot. All right. So that becomes a 1, and then I have it times cosine squared theta minus sine squared theta. So if I stop, I could stop here, totally fine. Nothing wrong with it. I could factor it a little bit more, as in, I could write it as cosine theta plus sine theta, or cosine theta minus sine theta. So it just depends on what we need. Okay. One other thing you could do that you won't see in your My Math Lab homework in section 7.2 is we know that cosine squared theta minus sine squared theta looks like Pythagorean, but it's a minus. Remember, that is a double angle identity for cosine. So we could just rewrite it as cosine to theta. Okay, so remember the 1 here was just multiplied by this. So 1 times cosine squared minus sine squared. So lots of options. Okay. Oh, fun times, rational expressions. All right. So if you haven't, I said how I posted a handout. There is also a video that I posted in D2L that I made quite a few semesters ago about simplifying rational expressions. So if you need to go back and watch that video for a refresher, or I'm sorry, not multiplying, subtracting, you can see that. Okay, so here's one with trig expressions. Okay, you will see stuff like this in your My Math Lab homework. So with algebraic expressions, notice how these denominators can't be factored. They're prime. Okay, so you want your denominators completely factored before you find the least common denominator. So least common denominator is a multiple of the denominators. Okay, this is very similar to this situation. If you have 1 over 5 plus 1 over 7. So what's your common denominator for 5 and 7? Well, if I look at 5 and 7, they don't have any common factors other than a 1, which doesn't help. So my least common denominator then is just the product of those two. So 5 times 7 is 35. So this is very similar in that a plus b and a minus b are both binomials. They don't have any common factors. Factors, remember, are things you multiply. So if a and b are not factors, a plus b is a factor. The other factor is a 1. Okay. So here, similar situations. Sine x plus 1 can't be factored. That's prime. Sine x minus 1, once again, is prime. So these two denominators don't have a common factor. So my least common denominator is going to be the product of those two. Oops, I better scooch down here. Okay, so my least common denominator is going to be sine x plus 1 times sine x minus 1. And I would not go ahead and I would not distribute that. We like our denominators and rational expressions to be factored. All right, now what we need to do is we need to get a common denominator, all right? So this denominator already only has this factor, sine x plus 1. So I have to multiply the top and the bottom by the missing factor. So basically, I'm going to multiply top and bottom by sine x minus 1. I don't have a lot of room there. So I'm just going to write it in the numerator. So I have cosine x. I need to multiply that by my missing factor of sine x minus 1. I'll go ahead and multiply in the next step. Okay. Here, my numerator is cosine x. So I have to multiply it by my missing factor. I have sine x minus 1. I'm missing the factor of sine x plus 1. So that's what I'm multiplying top and bottom by. All right, you must multiply the numerators. You do not want them factored because you can't combine them into 1. So I'm going to go ahead and multiply the numerators, distribute. So I end up with cosine x sine x minus cosine x. And then here, when I distribute, I end up with cosine x sine x, that's multiplication, plus cosine x. Okay, all over my common denominator. All right. Now, because I have a common denominator, then I can combine those into one fraction. Denominator stays the same. We subtract the numerators. So be careful here. You are subtracting both terms. So you have to distribute that subtraction through there. So I'm going to write it out. If you don't need to write it out, it's fine with me. Cosine x sine x minus cosine x minus cosine x sine x minus cosine x. So I distributed that minus. Now combine like terms. So what happens? Cosine x sine x minus cosine x sine x. These would add up to be 0. I have negative 1 cosine x, and negative 1 cosine x becomes negative 2 cosine x. Okay, now, great. But here's the deal. Because of identities, I can keep going. I can go ahead and multiply this denominator. Yes, I want to do it now, but I didn't want to do it earlier when I was working with getting my common denominator. Okay, that's a multiplying conjugate, so that's going to result in a difference of squares. So it's going to be sine squared x minus 1 and this looks very much, whoops, what's going on here? This looks very much like a Pythagorean identity. So my Pythagorean identity is cosine squared x plus sine squared x equals 1. So can I rearrange it so that I can get sine squared x minus 1 on one side? So what do I have to do? I have to move the 1 over here and the cosine squared over here, which gives me sine squared x minus 1 equals cosine squared x. So negative cosine squared x. So I can then replace this denominator with negative cosine squared x. All right, so I have negative 2 cosine x over negative cosine squared x. And then hopefully you can see we can simplify because I can take out a cosine out of the top and the bottom. And I can say a negative divided by a negative is a positive. So I still have a factor of 2 on top. But if I take the cosine out of top and bottom, I divide one out here and I take one out there. So I'm left with 2 over cosine x. Now you could stop there. Or, how cool is this? I can think of that as 2 times 1 over cosine x, which 1 over cosine x is secant x. So you could also write that as 2 secant x. The fun is limitless here in this whole identities world. Very cool. I love it. Okay, so I would like you to try this one. So pause the video, please, and see if you can come up with a simplified result here. Combine those two into one. All right, let's see how you did. All right, so common denominator is going to be the product of those two denominators. So it's going to be 1 plus cosine x times 1 minus cosine x. All right, so I have this factor. I need to multiply top and bottom here by the missing factor so that I'm multiplying by 1. Here I have a little bit more room to write it. So in the numerator, this one's a little nicer. 1 minus cosine x times 1 is 1 minus cosine x. Okay, over here, the factor that I'm missing is 1 plus cosine x. And so I go ahead and multiply the numerator. 1 times 1 plus cosine x is 1 plus cosine x. All right, and then we're going to subtract, combine them into one fraction. Denominator stays the same, subtract the numerators. So be careful when you subtract. If you're subtracting more than one term, you got to make sure you distribute. So I have 1 minus cosine x minus 1 minus cosine x, which simplifies to 1 minus 1 is 0, minus cosine x and minus cosine x is minus 2 cosine x. All right, and then in the denominator, I can go ahead and multiply this. Whenever I see these conjugates, I think if I multiply it, I might be able to get a cosine squared, which leads me to Pythagorean identity. So when I multiply that, I get a difference of squares. So it's 1 minus cosine squared x, which is equivalent to, that is a rearranged Pythagorean identity, which is equivalent to sine squared x. That's one of our most popular, 1 minus cosine squared or 1 minus sine squared. Okay, now here's something that's a cool little trick. So if you got to there, yay, pat yourself on the back. Here's where we can rewrite this. And you don't have to do this, but I think sometimes seeing it will give you this idea that this is doable. Okay, so I can rewrite it in more factored. So I have negative 2 times cosine on the top. And on the bottom, I have sine x times sine x, right? Sine squared x. So I can think of this as 3 different fractions being multiplied. This will be times 1. So it's kind of like this. It's negative 2 times cosine x over sine x times 1 over sine x. And I know then that I've got negative 2. Cosine x over sine x becomes cotangent x. And 1 over sine x becomes cosecant x. Okay, so if it ever says in the instructions, simplify so that there are no quotients, like we've seen before, this isn't good because that is still a quotient or a fraction. So, wow, that's fun. But yeah, being able to unmultiply things is a skill that to have in simplifying these expressions. Wow, love this stuff. Hope you do too.